Hi everyone, I'm Meng from Hefei University of Technology, and I'm happy to present our work, Repetitive, Oblivious, and Unlinkable SkNN over Encrypted and Updated Data on Cloud. This work is co-authored by Professor Mauro Conti and Professor Mamoun Alazab. As we know that smartphones are equipped with powerful sensors, including GPS. Mobile applications provide location-based services through sending the current location of a user and a geospatial query to a service provider. This provider searches its database and returns a query result to the data user. For example, Yelp, Google Maps, and Facebook enable their users to conveniently retrieve a list of restaurants, coffee shops, and hotels around their current location. But service providers always store their geospatial data on a public cloud, such as Dropbox and OneDrive, to enable lower maintenance costs, lower response delays, and greater flexibility. This, in turn, makes the user privacy a key concern since public clouds are not fully trusted. First, the cloud provider may covertly give or sell your personal data to third parties. Second, public clouds may have malicious insiders. The corrupted cloud employee engineer may steal highly sensitive data with the intention of giving this data to his new employer. Third, public cloud may be hacked and users' information will be leaked. In 2016, hackers stole 167 million email addresses and passwords from LinkedIn and sold them on the dark web. Therefore, it is vital to enforce privacy-preserving measures for location-based services and clouds. Also, given the data scandals in 2018, people are more aware of their privacy when using location-based services and other cloud services. The famous GDPR regulation has been effective since 2018. It marks a governmental attention and action on the user privacy in cloud services. To address this problem, secure key nearest neighbor SkNN query processing has been proposed and it is now widely adopted in location-based services, LBS. The SkNN query model is like this. A data owner stores encrypted data and a secure index on the service provider, while a data user submits an SkNN query to the provider, which returns a corresponding result after searching the local database. There are many noted prior works on SkNN and they are building towards an adaptively secure query scheme. Our motivation arises from real-world applications. For example, say a data user Bob submitted a S4NN query, location X, pizza shop, to the service provider, and received 4 results, namely Papa John's, Mr. Pizza, Domino's Pizza, and Big Pizza. Among the results he went to, he was quite satisfied with the Domino's people. Days later, when Bob is near the same query location and wants to dine at the previous Domino's Pizza. Unfortunately, Bob's memory of his shop somehow blurs and he submits a repetitive query to the service provider to find the preferred pizza shop. Our work focuses on matching a data item from the cloud repetitively in an oblivious and unlinkable manner after index updates and its privacy issues. Repetitive means it allows data users to query a previously matched data item even if the service provider has updated the index. Oblivious means it prevents the service provider from knowing that the data user submitted a repetitive query. Unlinkable means it prevents the service provider from knowing that the data item referred to in the repetitive query was a retrieved data item of the data user. To enable a repetitive query, we can introduce an identity to each data item. Before uploading the index to the service provider, the data owner has to append the identity to the location for each data item. When the data user queries the service provider about a previous data item, the user or the local application use the identity as the extra query condition. While matching the previous data item precisely, this approach, however, excludes other location-matched data items, which may expose the data user's requirements of repetitive matching. To match other data items, we cannot use this identity directly. Therefore, the technical challenge lies in the contradiction between using a preferred identity and matching other data items. The system model is similar to the traditional SkNN model, but we integrate data item identity into the framework of SkNN query processing and design a multi-level structure to organize locations. So basically, we have data owner and who submits multi-level structured location, identity, and data item to the service provider, while the data user sends the structured location and customized identity range to the service provider to retrieve a matching result. As for the threat model, we assume that data owners and data users are semi-honest, and the service provider is malicious. We formally define our 4 design objectives: functionality, privacy, security, and efficiency. For functionality, our scheme allows the users to query a previously matched data item even if the provider has updated the index. Second, privacy. We aim to provide strong data index and token privacy and achieve repetitive query in an oblivious and unlinkable manner. The third one is security. We should prevent the service provider from abandoning the preferred data item in case the provider colludes with a data owner to give priority to some locations. The last one is efficiency. We achieve 3 main objectives: low computational cost, low query latency, and low communication overhead. Our scheme is called ROU. We divide the scheme into 3 steps: index building, token generation, and query processing. First, we use the level-based space encoding to obtain location codes. We adopt the privacy-preserving range querying to generate identity prefixes for data items. Further, we integrate the repetitive query problem with location querying problem by mixing location codes and identity prefixes. Finally, we leverage IBFs to build secure indexes and achieve SkNN querying by membership checking. The data users decrypt and verify the received results. A data owner is holding a set of data items, DI, and pursue the random hash functions and another hash function, and secret keys. Each data item has type, location, and identity. We use DI as an example to show how to build an IBF in a leaf node. There are 4 levels in the pyramid-like structure from L1 to L4. All the levels refer to the whole service area, but they're divided based on different granularity. The data owner firstly converts location of DI into a set of grids from G1 to GL. From the second level to the L-1 level, we compute the hash of the level's grid number and then concatenate it with the level number. For the L's level, we convert the last level's grid number GL into a set of prefixes, and then convert DI's ID into a set of prefixes. Finally, we compute the mixed code MC by mixing the 2 sets of prefixes. For the L-2 levels, the data owner inserts each prefix LC into an empty indistinguishable Bloom filter, which is IBF. For the L's level, insert each prefix MC into an IBF. When processing all data items, the data owner obtains an N IBFs and builds an index tree from bottom to up. The non-leaf node's IBF and hash value is computed by its left and right children's nodes' IBF and hash values. The owner encrypts the .n data items by using AES encryption and asymmetric key SK to obtain ciphertext CT, and then computes a root hash value RT. Finally, the data owner submits to the service provider the index tree I and a set of random numbers, ciphertext, and RT, the hash value. A data user U is standing at location else and expecting to find the data item ID I. The data user firstly converts LC into a set of grids from G1 to GL, from the second level to the L-1's level. The data user computes the hash of the level's grid number and then concatenates it with level number like the data user did. The data owner did. For the else level, the user firstly expands current grid into a bigger area and computes a minimum set of prefixes M1 for the area. Then the user expands the current ID into a bigger range and computes a minimum set of prefix M2 for the range. Finally, the user computes a mixed code MC by mixing M1 and M2. Then the user computes pairs of twin location and hashes for the first I-2's levels as the first part of token, and computes pairs of twin locations and hashes for the else level as the second part of the token. The cloud server receives secure index and query token, and then it proceeds in two steps. First, check nodes IBF using T1. If this match continues until the leaf level, it means there's at least one data item matches the query on the first L-2 levels. Second, let a leaf node perform the similar query processing by using T2. If there's a match, the cloud server continues to search other matched leaf nodes. Finally, the service provider returns the ciphertext of matched leaf nodes and the proofs. For security analysis, we first define two leakage functions L1 and L2. We use the adaptive indistinguishability on the children keyword attack secure model and prove that the scheme is adaptively secure in the random oracle model. In the experiments, we used a real-world dataset and Python hashlib cryptography for the hash encryption. The number of data N ranges from 2,000 to 10,000, and the number of nearest locations key ranges from 1 to 5. The IBF size M ranges from 1.2 to 1 to 12 KB. The false positive rate is set to 1%. The number of pseudo-random hash function P is 5. For the performance of index building, we record the computational cost of building an index tree and the communication overhead of uploading the tree to the service provider. It shows that construction time and index size grow linearly with n. When n equals to 10,000, it costs the data owner less than 23 milliseconds in computing an index tree of 2.6 GB. The query processing time is a function of n and k. Figure A and Figure B shows that the query processing time is in the millisecond scale. When k equals 1 and n equals 10,000, the average query processing time for Orlando City is 28 milliseconds. The difference among the three cities are caused by the different distribution of matched data items. Figure C and D show the communication overhead. It corresponds to the returned leaf nodes. After the service provider returns the results and proofs to the data owner, the user verifies the results by recomputing the root hash value from the received hash values. It costs the data user in Orlando 0.08 milliseconds and 0.1 milliseconds when k equals to 1 and n equals to 2,000, and k equals to 2 and n equals to 10,000 respectively. We also compare our scheme with existing work, SkEQP and ServeDB. our scheme's average query time is smaller, and our scheme also has a good performance on communication overhead. So to sum up, in this work we have located the repetitive query in SkNN and have proposed a repetitive, oblivious, and unlinkable query processing scheme over encrypted and updated data on cloud. The novelty of this scheme is in realizing repetitive query by mixing customized privacy-preserving range query with SkNN query. We formally define repetitive query and its privacy objectives. We implement our scheme and evaluate its performance on our server and a real-world dataset. The results show that our scheme achieves practical efficiency. Thank you.